Well, thank you for coming. So this is the title of my talk, Security Stability Control of the Large Power Grids and the Microgrids. So I'm Xiaozhe Wang from Canada, McGill University. And I'm very grateful to have the chance to come here, supported by the International Excellence Grant at KIT. It's such a great opportunity. So before I start, this is the students I want to acknowledge who made important contribution to the work I'm going to present. All right, so here are three research directions. I have been working the past few years, so I'm gonna touch each one of the topics slightly. So part one is about uncertainty quantification and uncertainty-aware control for power system security, and the second one is data-driven methodology for stability monitoring and control, and the last one is cybersecurity study in power grids. Okay, so the first one, uncertainty quantification and uncertainty-aware control. While the motivation of the work is because of the continuous integration of renewable energy sources. We all know that this trend is going to continue in the near future because we want to develop net zero power grids to mitigate climate change, to develop sustainable communities and so forth. While the challenges of integrating renewables are obvious, right? So they're subject to the weather conditions. So the sun doesn't always shine and the wind doesn't always blow when we need the power, right? So they are highly variable, and the intermittency and uncertainty may affect the system in different aspects. So here is just a figure to show the uncertainty we experience in the system. We not only have uncertainty in the load side, which is what we have originally, but we also have the uncertainty on the generation side. Okay, so here's an example which actually from my PhD work. So in my PhD, we try to see how the uncertainty is going to affect the stability property of power system. So what we did is that we do the comparison. So this is the time domain simulation of the deterministic model, which will assume that the renewables are generating constant amount of power. While the right figure shows the time domain simulation results for the stochastic dynamic model when we consider the uncertainty from the renewables. So it's pretty clear that when we consider uncertainty, and the system may experience voltage collapse, which we didn't observe in the deterministic model. So this is a very strong argument to say that, you know, the uncertainty indeed may affect the stability property of system, and they need to be considered carefully in our study. So that's what the motivation of my work actually. So in the next few years, when I just started my career at McGill, we have been working on to analyzing the impacts of uncertainty on different aspects of the system, including security assessment, dynamic stability analysis. So in this work, I will focus on discussing the impacts on the security assessment. But if you're interested, I also put the reference that we investigated the dynamic property. Okay. All right. So I will start from the first one. So how the uncertainty is going to affect the system available transfer capability. Okay, so then the first question is, what is available transfer capability? And it is related to another concept called total transfer capability. It refers to the amount of power that can be transferred from one area to another area through a path in the transmission network in a reliable manner in both the pre-contingency and the post-contingency. Maybe I can, yeah. In both the pre-contingency and post-contingency system conditions. So for example, if we want to transfer power from Quebec to Ontario, right? So we want to make sure that the power transfer is carried out without meeting the stability limit, the voltage limit, and the thermal limit, okay? And as the power system is evolving, it's changing all the time, you can imagine that the total transfer capability needs to be assessed from time to time. Okay, and then what is available transfer capability? So usually when we calculate the total transfer capability, we will deduct it by 3 margins. One is the existing transmission benefit margin capacity, which is the ETC, and the other one is the capacity benefit margin CBM. Okay, so these are determined by, for example, the utility market model or base power flow, which we just regard to be deterministic value in this work. But there's another margin which is very interesting. It's called TRM. So it's the transfer reliability margin. It is reserved to account for the uncertainty of the system from different aspects like load or system topology change or whatever. So all this uncertainty needs to be considered. So we typically reserve a margin just for that reason. Okay. Yeah, so this is how we calculate ADC conventionally. Well, in our opinion is when the renewables are coming to the system, it becomes highly volatile. And rather to assess everything in a deterministic framework, we believe that we need to use a probabilistic framework to assess the TDC and ADC. So how does it work? So when we have the renewables and everything coming in, and then the TDC is no longer a deterministic value, and rather it's a random variable that may exhibit certain distributions. Okay, and then the TRM, we believe it should be reserved, for example, by the difference between the mean value of the TDC and the 5th percentile of the TDC. So this amount should be reserved to account for the uncertainty, and as a result, we can get the ATC available transfer capability with certain confidence level, for example, 95% confidence level. Okay, so this is what we think that we should assess the TDC and ATC. So from this picture, I think it's very clear. In order to do that, the key thing is that we need to get an accurate estimate about the TDC distribution of the total transfer capability. Okay, and then how to do that? Okay, so let's firstly consider how we actually assess the TDC. It can be done in different ways: repetitive power flow or continuation power flow. For example, this is what we adopt in our work. So how does it work? It's like the PV curve. Okay, you may recall what we learned in our courses. It's a PV curve. So along a certain path, right, we increase the power step by step. As we increase the power, we may first meet the voltage limit. For example, the voltage at certain bus drops too low. And then if we keep increasing the power, we may meet the thermal limit. And eventually, we may meet the static stability limit, which is the nose point. Okay, so along the way, right, we are trying to find the minimum, the maximum lambda we can go without violating the limit. So basically, this is the mathematical formulation of that. So we try to find the maximum lambda we can increase along the path without meeting all the operation limits. So this is the continuation power flow. And if we have a contingency list, then we have to carry out this computation for each post-contingency case. And the minimum lambda that we get from all the cases before contingency and after contingency will be the total transfer capability for this particular case. Okay. And then when the renewable comes in, it becomes more complicated because we are going to have random variables coming from wind speed, solar radiation, low power, line outages. So you can imagine if I want to get an estimate about the probability distribution of lambda, which is the TDC, the most straightforward way is to do Monte Carlo simulation, but it's gonna take a long time, right? So it's gonna take prohibitive computational efforts, which is not practiced in real world. So what we propose in our work is that we're going to use the polynomial chaos expansion. I know some of you may be familiar with this method because you're also working in this area. So we use the polynomial chaos expansion to effectively and accurately estimate the PTTC. Okay, so originally with McGill simulation, how it works is like we generate a large number of random inputs, scenarios, and we feed them into the physical continuation power flow model, like what I showed here, and they're going to give you the response. And you can do a lot of simulations and to plot the histogram, right? Well, the PCE will do it in a different way. So it will firstly generate some small sample and feed into the physical model to get the response, okay? And from the small number of evaluations, we are trying to build a surrogate model, which can describe the relation between the random inputs and the output by expansion of the polynomial series. Okay, so this is how it works. And once we get this model, and then to assess the model response is gonna take negligible time. We just generate the samples and we substitute into this model to get the model response Y. Okay, so this is why it saves time, because this model is just an algebraic model. Once you get this model and then evaluate this model takes no time, right? We only need to get a very small number of samples evaluation at the initial stage. So this is how it works. So well, there are two things, right, to build this model. One is to construct the basis, and the other is to calculate the coefficients. So to calculate the basis, right, there are different ways. If we know the distributions of the random inputs, then we can just use some standard polynomial to build the basis, like what is shown in the table, normal distribution, uniform distribution, and so forth. And even though the distribution are not in this table, but we still have what is so-called Stieltjes procedure that we can utilize the orthogonality to build up the basis. Okay, so this has already been studied. And in our work, so the question we have in mind is, what if we have no idea about the marginal distribution of the random inputs, which might be the case in practice, right? We only have the raw data. We don't really know their distribution, and the distribution of parameters may change from time to time, from season to season. So can we build the polynomial basis using purely raw data? So this is the question we have in mind. And indeed, right, so this is what I got from the Unreal website, that accessing raw data nowadays is not hard. Thanks to many initiatives, we have open data. All right, so in this work too, we use what is called the moment-based polynomials to build up the polynomial basis. So it turned out, yes, that we can simply use the raw data, and by using the condition that the polynomial bases are orthogonal to each other, we have shown that the coefficients for the polynomials and the raw moments of the data satisfy this condition. Okay, and then it means that we can only calculate the raw moment of the data, and then we can calculate the coefficients. And with the coefficients, we can build up the univariate polynomial basis. And then using the tensor product, we can calculate the multivariate polynomial basis, right? And this is what we propose in our work too. This is a data-driven PCE methods. And once we build up the polynomial basis, and then the remaining task is just to calculate the coefficients for the model, and there are different ways to do that. We adopt an advanced regression methods called least angle regression, just to calculate the coefficient. All right, so this is how it works. Just to recap, so we generate a small number of scenarios, we feed into the model, get the response, and based on this, we try to build up the surrogate model. And then once we have the model, we can just generate a large number of random inputs to get the model response and plot the histogram. Just to show some simulation results, this is what we do in a 118 bus system where we consider 111 random variables. 6 come from wind, 6 come from PV, and 99 loads. And the transaction under study, we consider the power transfer from the generator at these buses to load at these buses. And the TDC assessment 2 is the VSAT in DSA2. So DSA2 is the commercial power system analysis software. I think it's what they use in both industry and academia. Okay, so we firstly compare the PDF, the probability density functions, and the cumulative distribution functions estimated by the sparse PCE, the conventional PCE, and the data-driven, marked by the red one, data-driven sparse PCE. So we can see that the CDF and the PDF can both be accurately estimated. And then we compare the computational efficiency. So the Monte Carlo simulations using the Latin hypercube sampling methods, if we have to run 10,000 simulations, it's gonna take you 173,000 seconds, okay? But if we use the data-driven sparse PCE, and most of the time is consumed by generating, the small number of sample simulations and model response. And once we generate that, building up the model and the sample evaluation takes very little time. So in total, it takes around 9,370 seconds. So it's around 18 times faster than the Monte Carlo simulations. And another interesting thing we observe is that, for example, if we just adopt the deterministic framework to estimate ATC, so we reserve 5% of the TDC to be the TRM, right? And then it will be around 6 megawatts. And the resulting ADC is 132 megawatts. However, if we use a probabilistic framework, if you still remember that we use the mean difference between the mean value and the 5th percentile of the TDC as the TRM, okay? And it's gonna be 49 megawatts, and the ADC will be 90 megawatts. So it means that when we considered uncertainty of the renewables and all the loads in the system, then ADC needs to be reduced by more than 30%, which is a very significant amount, okay? But what I'm saying is that it's not always reduction, right? Sometimes it might be even increase, but we just want to get a more accurate estimate of the ATC so that you can ensure the system security in the meantime to fully utilize your transmission asset, right? Because this is the power transfers actually means money, okay? All right, so this is the PCE methods. It has a sound mathematical basis, and it can be integrated with deterministic analysis too in a non-intrusive way. And it can be with sparse scheme, it can be fast and accurate. And there are some additional advantage of the data-driven PCs that we have no pre-assumed probability distributions. We use data directly, and we can consider both continuous and discrete random variables in our study. All right, so after this work, we realized that the PCE might be a very effective uncertainty quantification method to quantify the probability, the uncertainty propagation from the inputs to the model response, and it can be applied in different applications. So, here it just some examples of the applications we can consider. So those ones marked in red are something we have already studied in our group, and there are also some other things we're going to investigate. Like probabilistic power flow, for sure, economic dispatch problem, the stability index, the microgrid power support, okay? And for different applications, the different thing is only the physical model is gonna be different, right? And the methodology can be universal. So, for example, we consider how the uncertainty is gonna affect the economic dispatch cost. And in this problem, right, then the model response will be the cost, the minimum cost of the economic dispatch. So we're trying to dispatch the conventional power, the power output of the conventional generation while considering the uncertainty from the renewables. So this is basically the model formulation. And in this case, as I said, the model response rather than TTC will be the cost, minimum cost of the dispatch. And we consider integrated energy system. We have 118 bus system integrated with a 20 node gas system. So it's the integrated energy system. And in this study, we consider 120 random variables, 5 coming from wind farms, and it's in 24 hours. And total installed capacity is about 12.3% of the total capacity. All right, so again, we firstly compare the estimation results for the CDF and PDF. And both data-driven sparse PCE and sparse PCE can give pretty good accurate estimation. Well, in this case, you might observe that, you know, the distribution of the cost is kind of irregular compared to the TDC. So it's kind of multi-model. You know, it's not like clearly a Gaussian distribution. So at the beginning, we were concerned that the PCE may have some challenges, but it turned out that it can still give relatively good estimation results. And also here, just to note that we use the real data from the Unreal website for the wind. Well, the last study, we used the emulated data, but in this study, we try using the real wind data and try to see how it works. And also we compare the computational efficiency. Again, you know, if we only want to get good statistics like mean or the variance, actually the PCE just requires 300 simulations to provide this accurate results. However, if we want to get very accurate, like PDF and CDF, we need a little bit more number of simulations, like more than 1,000. But no matter what, that is a lot faster than the Monte Carlo simulations. Okay. Also, we also investigate another surrogate modeling methods, which is called low rank approximation methods, and we apply that methods to probabilistic powerful problem. So low rank approximation methods may have a better scalability, but I think in the generally speaking is pretty similar to the PCE. Okay, and we try to estimate it's like a powerful solution, the PDF and CDF. And there's also one interesting observation here is that if we just run the deterministic power flow, and we can see the deterministic power flow solution is well below the thermal limit, which is right here. Okay, it's well below the thermal limit. However, when we run the probabilistic power flow, which means we consider the randomness from the renewables, from the CDF, you can see that actually there is 40% probability that, you know, the branch power flow may violate the thermal limit. So it's another important observation to show that, you know, we have to consider the uncertainty, especially when we have more and more volatile renewables in the system. It may affect the system security and operation in different aspects. Okay, so this is the insights and conclusions. So we have seen the detrimental impacts from the randomness of the renewables, loads, and line outage. They may affect the transfer capability, and we may have a high probability of violating the operation limits because of that. And on the other hand, we see that, you know, the utilization of the uncertainty quantification methods may be very helpful to advance the development of a probabilistic framework for secure operation and stability assessment of power system. So this is what we want to promote. So there are also some current and future interesting work is that we have already seen the negative impacts of the randomness, right? And then the natural question is that how can we mitigate, right? How can we mitigate those detrimental impacts? And for example, if a system have hundreds or thousands random variables, right? Are there just probably just 10% of them are the critical ones? For maybe, you know, by smoothing out their variability, we can increase the system performance in the most effective way. right? So that's the question we want to say, okay, among 100 or even 1,000 uncertainty sources, can we pinpoint the most critical ones? So it turns out, yes. So we use what is called the global sensitivity analysis methods to do that. And PCE methods can also help us to quickly calculate the global sensitivity index. So for example, the Sobol index, which is mathematically given in this way, it quantifies the effect of varying of particular random inputs on the variance of the output. Okay, or intuitively speaking, it means that if a random variable has a very high Sobol index, it means that varying, this particular random input is gonna affect the variance of the output very significantly. So it means that it is critical. Okay, so by calculating the Sobol indices of the random inputs, pinpoint the top ones and smoothing them out, we are able to improve the system performance in the probability sense. So this is what we did. Okay, so the Sobol index may only work for independent random inputs, but when the random inputs are correlated, we also use analysis of covariance and cova indices to measure the importance of the random inputs with respect to the variance of the output. Just to give you an example, so this is another application we consider. It's about the microgrid ramping support capability. So what we consider is that the microgrids can improve the system stability and resilience, right? And we are also discussing whether they may provide auxiliary service to main grids, because we have a lot of renewables in the microgrid and distribution system. Despite just working on their own, they may even provide service to support the main grid during heavy load period, for example. So in this study, we consider the ramping support capability, which is the amount of power that the microgrid can provide to the main grid, okay, during some heavy load period. So the ramping support capability, you can consider it as a service of the microgrid, right? And the randomness of the renewables inside the microgrids may affect the service quality, right? Because the amount of power that can be provided may also be affected by the uncertainty of the microgrids itself. So our question is how the randomness of the DERs may affect the ramping support, and how to use the energy storage that may help us increase the quality of the ramping support capability of a microgrid provided to the main grid. Okay, so what we did in this work is we applied the data-driven PCE methods to efficiently assess the probability characteristic of the ramping support capability. I didn't show the results because it's kind of very similar to what I just showed for the total transfer capability. But more interestingly, we calculate the Sobol indices of the random inputs. So the x-axis refers to, the random inputs. We have PV, we have wind turbine, and we have EVs, okay? And we all use the real data for the random sources. And the y-axis is the Sobol indices, it's the global sensitive indicators. And we're trying to assess the indicators for different hours, okay? 1, 3, 5, 9 a.m., like in a 24-hour horizon. Okay, some interesting things is like before 9 o'clock, right? So the PV play no role. Their indices are just 0, which makes sense because it's midnight. There are no power solar output, right? And around like 11 o'clock, you can see that the PVs are important. There are 2 PV here, their Sobol indices are very high. It means that they are the critical random inputs. Yeah, so this is pretty intuitive about PV, but some other random inputs may not be that intuitive. For example, the EV, okay? So the EV here at 9 o'clock, right? they're pretty high, but at some other hours, in the midnight, right? So the middle two are important, and the 11 o'clock is the first and the last one are important, right? So it just means that without doing this analysis, you can hardly, hardly measure the importance of the random inputs. But by doing this analysis, we can actually pinpoint the critical random inputs from time to time. And then by smoothing out their randomness, okay, which means reduce their variance to 0, just to keep the mean values, okay, using the energy storage system. And we can see that we can narrow the probability distribution of the ramping support capability a lot. Okay, so in the probability sense, it means that we can increase the ramping support capability, right? The amount of power that the microgrid can support a main grid, like in the probability sense, without adding additional energy storage system. We just add like a control to control the variability. We just don't add, additional energy storage. We don't increase the capability of the BESS. Okay, but just by controlling the variability, we can do that. So this is the increase the ramping support in the base case, and this is after the second row representing the ramping support capability after implementing the energy storage system, and this is the improvement. Okay. All right, so this is what we have done by far, and this is something we are currently working on. It's about power system resilience, right? How the power system is gonna respond under extreme weather, which is a great deal in North America. Like, we have experienced more frequent and severe extreme weathers, like freezing rain or snowstorm, and people are very concerned about how resilient our critical infrastructure is when subject to these extreme weather events. And you can imagine that it's gonna be, it has to be assessed in a probabilistic framework, right? And extreme weather is actually like a low probability but high consequence events. So basically they sit in the tail of the probability distribution, and how to accurately capture them, estimate them is very important. So this is what we are currently working on. Okay. So here comes the second part, data-driven methodologies for stability monitoring control. So in addition to the challenges, I just mentioned, which is the uncertainty coming from the randomness from the renewables. We also have other challenges that we have power electronic converters integrating into the grid, right? And they have very different dynamic response compared to the conventional generation. And here it just like results from a previous work, which actually show that when the penetration of the converter interface generators increase, the damping performance of the system is gonna be deteriorated. So various control modes of the CIGs and their distributed installation introduce complexity and uncertainty to the system model, parameters, and topology. So this is another challenge we're facing right now. But at the same time, our power systems are installed with more sensors, accurate and highly sampled sensors like PMU, and they are able to provide like voltage, current fixtures, and frequencies, and they offer a unique opportunity for us to develop, data-driven methods which can complement the conventional model-based methods. So that's the idea. So if we consider the conventional, stability monitoring and control methods, I would call them as white box methods, because they require, all the detailed models, physical knowledge, and everything, right? So their limitations are also obvious, because we cannot always have accurate model. And our system, have changing operating conditions, and the topology information may be outdated. And rather that, people come up with what I call black box methods, which is like, so purely depends on data, right? For some example will be the system identification approach, right? So I have, your system, I have the input and I have output, and I'm trying to build up a state space model to describe this mapping. Then the problem are also obvious because, you can hard to interpret them physically. They're not the true system model. And as a result, it may be very hard to perform control and may not be robust and adaptive. And recently, right, we have a lot of like learning-based methods to carry out the control of a system, reinforcement learning, for example, but they require a lot of data, extensive training, and there may be problem, if the system undergoes untrained scenarios, for example. So what I do in my group does is try to build a bridge. Okay, we're trying to come up with methods which I call as gray box methods. So we try to utilize the data available in the system, but in the meantime integrate the power system domain knowledge. Okay, as a result, we can develop online adaptive identification and control methods that are robust and adaptive to system topology, and also, more importantly, require no warm-up training, offline training. So they can be, just implement online adaptively. So this is the goal of my group. So in this area, we have, consider many different applications. We have developed online data-driven methods for wide area damping control, for secondary voltage control, for inertia estimation, dynamic load model identification, locating the force oscillations, right? So especially when the oscillation frequencies are resonant frequency, you can experience you can see a lot of oscillations, but you can hardly pinpoint the source. And we have also worked on the voltage and frequency control for microgrids. So I'm gonna just talk a few applications, given the time. First is the wide area damping control. So because we have the inter-area oscillations, I'm not sure if you're familiar with that subject, right? So it's a long-lasting, I think, research topic in academia and also in industry. They have seen that two areas are oscillating against each other, and local damping is not going to work. We really have to take the system, consider the whole system, and to carry out the control systematically. Okay, so the theoretical basis of the methodology we develop is as follows. Okay, we assume that in ambient conditions, that the power system dynamics can be described by the stochastic differential equations. Okay, so particularly we have, this is state variable, system state matrix, but the Xi is a Gaussian random variable describing, the stochastic variation in the system coming from loads. Okay. And here you may notice that the system matrix, dynamic state matrix A is a very important matrix, right? It carries a lot of information like your oscillation mode, your topology information, inertia, damping information. A lot of more information are embedded in this matrix. So just give you an example, right? The classical model of the synchronous generator. So this is just swing equations. Power engineers may be all familiar with that. And then the A matrix will take the form like this, right? If you linearize the system. And then the M is the inertia, D is the damping, and here is the Jacobian matrix. Well, the PE is the power injection, right? Or the electric power injection of the power generator to the grid. And it highly depends on the system topology and line impedance, right? We have the G, conductance and susceptance. So basically what I want to deliver here is A carries a lot of important information, okay? And then in our work, we have shown that when we consider the load variations in the system, and then the swing equations can be approximately represented in this way. So compared to the conventional classical model, we have a stochastic perturbation term here to describe the load variation. And then if we linearize that equation, we obtain the stochastic differential equation, which is actually a multivariate Orson-Uhlenbeck process, OU process. And then we utilize an important property of the OU process. It says that if A is stable, okay, then the regression theorem of the multivariate OU process says that the correlation matrix is governed by this differential equations, okay? And particularly here, the G is the tau lag time correlation matrix that be calculated in this way. So it's a statistical matrix. And particularly, it can be estimated from PMU measurements, okay? So if you have PMU measurements, you can get their delta, omega, and then based on that, you can calculate this matrix. And then by solving 5, and actually we can get the A matrix from the tau lag correlation matrix, okay? So the important message here is that this important dynamic system state matrix A can be estimated purely from PMU measurements without any knowledge of the dynamic model parameters and without the network parameters, okay? So that's the important insights here. So by solving this, utilizing 6, we can, obtain this matrix from PMU, and then we can get a system state matrix, which is the true system state matrix. All right, so utilizing this is their theoretical basis for the very simple swing equations. But if we consider the CIGs, the converter interface generator, there's something we have to, analyze that the PEs no longer just depends on delta, but it also depends on the power injection from the CIGs, okay? And by some mathematical, calculations, and we come up with this model, okay? We arrive at this model. And by utilizing the regression theorem, again, you can estimate this matrix, okay? But it's not sufficient to carry out wide area damping control, because what we want to do is to adjust the reference of the CIG in order to damp the oscillations. So what we want is to have, a closed loop expression. So we also need to estimate this matrix so that we can carry out the control to change the delta PV, okay? So there's something that we have to carry out, but I'm not going to go to the details. So in this work, we actually use the regression theorem of the multivariate OU process and a perturbation approach so that we can estimate, all these matrices marking in red specifically. So then we can get the A matrix and B matrix, and then we can carry out the control. So that's the idea. Okay, so advantage, we can estimate a true matrix, which possesses a very clear physical interpretation. And also our design methods seem to be the first model-free methods that can achieve full decoupling of all the modes, okay? Because there are also other wide area damping control, but their matrix they estimate is not a true matrix, so they cannot guarantee the full decoupling of the modes, but we can guarantee that. So here's a study. I just didn't go into the details, and we estimate each one of the submatrices, and we can see it's very accurate. And we can carry out the control. We want to bring all the critical inter-area oscillation modes to the well-damped region, and we can do that. Yeah, so I give the reference. If you're interested, you can go into the paper. And also, we are utilizing this methodology to estimate the inertia, okay? So we have some mathematical manipulation, and we show that when the system with CIG, and the X state variable needs to be, it looks like this. We have some state variable coming from the PLL as well. And then the system dynamic state matrix A will look like this, okay? And then the inertia constant of the synchronous generations and the information about the virtual inertia constant of the CIG are all embedded in this small some matrices that we want to estimate and extract. Okay, so this is the idea. And then, so the advantage is that we can, estimate the virtual inertia constant for both the CIGs and equivalent synchronous generations without introducing large disturbances. So this is actually compared to the state of art, right? So we are not the first one considering this problem, but we're trying to see what are the advantage of our method is that we can do it in ambient conditions, and we can simultaneously estimate their inertias. And also we have demonstrated they are robust to measurement noise, missing measurements, and different operating conditions. All right, so this is just the simulation we consider. As in a 68 bus system, we have 3 CIGs. And then this is the inertia estimation without considering measurement noise. And this is considering the measurement noise. And also we consider there are some missing measurements from some generations, but we can still estimate the rest of the inertia of the rest of the generations. And then we also consider how to test the adaptiveness of the methods when topology change or when the inertia constant, change from one value to another value. I think it may happen for CIG, especially when you change your control modes or when your power capacity change and the inertia constant will change, right? But it's very important to get an accurate estimation of the inertia because otherwise you will have a problem predicting the frequency response of the system. For example, here we show that when the inertia constant of a CIG change from 5 to 50, and then the frequency response of the conventional generation will also change, will also be affected by the inertia of a CIG somewhere else. So it means that you have to, if you really want to ensure the frequency stability of the system, you really have to get very accurate inertia information for all the generations and CIGs. And also important thing is that when, the CIG in virtual inertia is 50, we can see significant improvement in the frequency response. All right, so this is all the methodologies and the application we developed based on the OU regression theorem method. And there are some limitations you may realize. So firstly, they only work in ambient conditions. One, the A matrix is stable, right? So that's the assumption of the regression theorem. So the question in my mind is that how about, what if we have large disturbance, right? How do we ensure the stability of the system under large transient despite modeling accuracy and complexity? Especially in the microgrids, we have, different operation modes and, their control modes may be very complicated. And then how can we handle the complexity? And also there are low inertia and nonlinear, and all these are the challenges of the microgrids. So this is a control structure of the microgrids, right? Oh, wait, yeah, okay. So we have primary control, right? Which describe the fastest response of the DERs under large disturbance. And we have the secondary control, which take care of the voltage restoration, frequency restoration, power sharing. And we also have tertiary control, like coordinate different microgrids, for example. So our work focused on the secondary control. We try to analyze, we consider the voltage and frequency control and restoration under large disturbance. Okay, so the problem formulation is that we consider that the secondary control of the microgrids can be described by the conventional Joule functions. Okay, the Joule function is just like, okay, how the power and reactive power varies is going to affect the angle and voltage, okay, at the buses, at terminal buses. And the secondary control actually is trying to adjust the reference power P and Q so that, I can quickly restore the voltage and frequency to their nominal values and their disturbance. And again, the P and Q are the real power and reactive power injections, which depends on the system topologies, right? System network information. We have the conductance and susceptance here. Of course, there are existing data-driven methods, and the PI control would be the most commonly applied data-driven methods. But our argument is that it may not be effective when operating condition and the system topology change because they're only tuned for a specific base case, right? And when your system operating condition change, that may change. And also there are learning-based methods, as I said, it may require a lot of data and offline training. So what we did is to develop methods based on a Koopman operator theory. Okay, so the key idea of the Koopman operator theory is that it can transform a nonlinear dynamical system into an infinite dimensional linear system under a Koopman embedding mapping. Okay, so and after you transform a nonlinear system to a linear system, right? The advantage is that all the well-developed control methods for linear system can be applied and with guaranteed stability property. Okay, so that's the advantage. So the Koopman operator theory says that under embedding G is like a mapping G, and then the Koopman operator K will advance the embedding G linearly in the Hilbert space H. Okay, so we have to find the mapping G, and under this mapping, that system is gonna advance linearly. And in microgrid secondary control, we consider an approximation Koopman in the form of extended dynamic mode decomposition with control. So we assume there's a mapping G, nonlinear mapping G, and then under this mapping, the system can advance linearly. So it's a linear state space model. And it can describe both small signal linear dynamics and large signal driven nonlinear dynamics globally. So the main tasks are as follows. 3 main tasks. Firstly, we need to find a proper Koopman embedding G. Okay. And that what we do is to use power system domain knowledge. Okay. And then we develop iterative learning based algorithms to identify the matrices AC and BC. Okay. And after that, we can apply, just LQR to carry out control for voltage and frequency. Okay, so let's recall the Joule functions I just presented, which describe the dynamics for the secondary control, and we have the real power reactive power injection here. So firstly, the basis selection is the mapping, okay? Well, naturally, if we linearize the system, right, and then we would have delta theta and delta V, and we would have a linear basis model, which is good to describe the small signal dynamics, right? But not under large disturbance, under linear, small disturbance. And then I want to find another model that can help me describe the uncertainty and nonlinearity. And then by observing the P and Q here, okay, we realize there are a lot of trigonometric terms, right, coming from the power flow. This is the where nonlinearity come from, actually. So in the mapping, we include sine delta theta, cosine delta theta, and also the frequency into this mapping. We call it Koopman observables. And then this is the nonlinear basis model, and we hope that it's gonna be beneficial to describing the large signals. So we have a linear basis model, nonlinear basis model, and our question is like, how can we seamlessly, combine the two models so that we can describe globally the system dynamics? So we firstly introduce an adaptive matrix just to CM, which is just to approximate the mapping between the linear basis and nonlinear basis. So this is something that we can calculate, at each time instant when we have the observables. And then we assume that the final state variables, right, can be represented by a weighted sum of the state variable from the linear basis model and the nonlinear basis model. And here is the, a weight beta, okay, which is a very intuitive idea. But the question is, you may have is that how do you know beta, right? What is the value? Does it make sense to just assign a fixed beta? I don't think so. So we, after some mathematical manipulations, we actually arrive what is so-called ensemble Koopman state space model. So this is how it looks like. And for the state variables, we have linear basis of state variables, nonlinear basis state variables. And what we need to do is to identify AC and BC, okay, so that we can have the model. And the question before is how to identify A, AM, and beta, okay? But, you know, we just don't want to use fixed beta, okay? And then to identify A, AM, I don't think it's a good idea. So when we arrive at this model, the key thing to do is to estimate AE and AEM, which actually are a function of A, AM, and beta. Okay, we don't. So the idea is that we're not trying to estimate, you know, assign a fixed beta and trying to estimate A and AM separately, but rather we use the iterative learning methods that try to estimate AE and AEM. So how it works is like, okay, this is a PMU measurement, okay? And then after this nonlinear mapping, embedding G, this is the Koopman observables. We have linear basis, we have nonlinear basis. This is something we can calculate from the measurements. And then we're trying to, then we can get a CM describing the mapping. And then we have an iterative learning mechanism. So we assume AEM is fixed and trying to use regression to get AE. And then we assume AE is fixed and trying to get AEM. So we do it iteratively until the regression error is small enough. Okay. This is just the key idea of the methods. I know is details has to be, you know, we have to look into the paper about all the detail, but this is the idea how we do that for system identification. All right, and then once the regression error is really small, we can get our Koopman ensemble model, right? And then we can carry out control. So that's the key idea. All right, so the advantage of this method is that we have shown mathematically that this adaptive Koopman operator optimal control method is BIBO stable, bounded input, bounded output. And we also provided sufficient conditions for the asymptotic stability of this control methods when subject to large disturbance, okay? And this method is well characterized with well-characterized stability property due to the linearity of the Koopman operator. And it's data-driven and require no warm-up training, right? So this is the advantage. And especially, I think, you know, compared to the learning-based methods, we have a well, you know, proved stability property, which is definitely the advantage. So these are just some simulation results. We have considered 4-batch system where we model all the inner loop, outer loop in details. But you may imagine it takes a long time for simulation. So we also consider a 34 node test system where we only model the secondary dynamics without, you know, the inner loop dynamics. And we have done testing both systems. So this is just some simulation results. So we firstly try to see how the ensemble Koopman modeling helps in, you know, just predicting the trajectories. So this is the prediction arrows, okay? When we have a large disturbance, we try to compare how the full basis with ensemble, and full basis means like linear basis, nonlinear basis, but without ensemble, which means we just assume the weight is 1-to-1. They're, you know, 50-50, and then just linear basis. So you can see that with the full basis ensemble, we have the lowest prediction error under large disturbance. And then we also compare the control performance, see how the full basis with ensemble can, you know, perform in terms of restoring voltage and frequency. So the first figure shows the performance when there's no secondary control. So the voltage cannot be restored. And the C here, it shows the control with linear basis only. So which means despite large disturbance, we just use a linear model, how it works, okay? The voltage can be restored. However, you know, it suffers from large fluctuations. And then this is the one that we use the full basis, but without ensemble, which means it's just 1-to-1. And then it's a little bit better, but still we have fluctuations. And then the proposed one, you know, has the smallest fluctuations, and we can restore the voltage and frequency. Yeah, so this is some comparison with secondary PI and secondary Joop, and this is the runtime, just to show that it can be implemented in real time without any problem. All right, okay. All right, so some current work we are doing is that we're trying to develop Kuhlmann-based methods that can extract the true model. Again, the methods we just developed is a system identification approach, right? We integrate domain knowledge, but still we cannot guarantee the model we identify is the true model, and we are working on extracting the true model so that it can, the methods can still work well in unforeseen, untrained, specific, like very weird contingencies. And we also working on develop data-driven modeling methods for aggregate EV so that we can do charging scheduling or V2G frequency regulation. So this is something that we're currently working on. So what we have done is that we have designed new false data injection models targeting state estimation, targeting AGC, automatic generation control. And then we have also, work on load redistribution attacks for integrated energy systems. So I will briefly introduce the AGC. I think it's kind of relevant to the second part I just presented. So this is, the control block of a two-area AGC system, right? Automatic generation control, which is critical to maintain the grid frequency by adjusting the output power of the selected generators, okay, as the load change, because the load varies. And then this area 1, area 2, they are represented by the equivalent generations, and they're going to send, the frequency and the timeline power to the control center through the communication system. Okay, and then the communication system, the control center will, based on the measurements, to calculate what is called ACE, area control error, which is a linear combination of the measurements and timeline power. And based on that, they adjust the power generation output for each area just to make sure, the frequency is maintained at the nominal values. So this is like the frequency control, and this is the, the dynamic equations for AGC system. Again, we are utilizing the multivariate audio process. We're trying to see whether by listening only the measurements, okay, whether we can extract some key parameters from the system. And then based on the estimated parameters, we can design a stealthy attack, try to, interrupt the operation of the system. So that's the idea. Very similar to, the data-driven. One is to stabilize, one is to destabilize. Again, so this is, it's not regression theorem. We also derive what is called maximum likelihood estimation for the multivariate OU process. We have actually shown that the estimate A obtained from the regression theorem actually correspond to the MLE, maximum likelihood estimates. And also here, sigma actually is a covariance matrix of X. It's like, the variance intensities of the states. Okay, so we are going to do that. Okay, so there are some practical consideration that first, there are some internal variables we cannot actually access. For example, the PG and PM, the turbine, right? So this is not something transmitted through the communication network. They are not accessible. But by some approximations, we can still show that by only listening to the transmitted measurements, we can still estimate the key parameters here. And these key parameters are sufficient to interrupt the operation, because if you look at the PREF, okay, it only depends on the P and V and Ka, which is the integrator gain, and also the frequency bias factor, which is AGC parameters. We can extract from there, and this is the incidence matrix describing the topology connections. So by estimating the 3 parameters, we can somehow to estimate the delta P ref dot, okay? And then what we do in the next is that we come up with this attack design. So we're trying to minimize delta P dot subject to these conditions. So these conditions is, firstly, your ACE cannot be too big. And so the one with the tilde is the injective values, like attack values. So after the attack, your frequency also cannot be too big. And target power as well, because there are bad data detection rules in the control center, right? They are going to check. If these are too big, they will say, oh, this is very suspicious, and they will just block the data, right? So from the intruder perspective, we don't want to do that. So we want to interrupt the operation while remaining stealthy. So this is the idea. So we want to reduce the generation output in a short period while remaining stealthy. Yeah, so this is a summarization. So we have eavesdropping stage, we listen the measurements, and we use the MLE to extract the parameters, and then we are going to design the attack vector according to the minimization formulation, and we're going to inject until the frequency reduced to 59.5 hertz. Okay. And advantage, so this method seems to be the first parameter-free stealthy FDI algorithm. So we're not the first one, doing this research, but in the past, they all assume the intruders have access to the parameters, okay? They assume the intruders knows the generation model, knows the AGC parameter, so they can do something. Okay, but our work actually showed that, the intruder may not even know this. They can still interrupt your system, destabilize your system. So that's the key novelty, I would say. So here is just like a very brief results. So firstly, the red lines represent the manipulated values displayed in the control center. Okay. Which we can see is the red one. It's very normal, right? It looks very normal. It's always in the bounds. The green line is the bounds by the conventional BDD. You cannot observe anything. However, the blue lines are the true ones. Okay, we can see that the frequencies start dropping. The ACE also goes beyond the bound. However, this will not be observed by the power operators. Okay, and then you can see by certain time that it will drop to the critical value 59.5 hertz at 105 seconds. Okay, and that will be very dangerous. So this is the idea. Yeah, and also currently we're working on the code simulation. Like we're trying to model the power system in HyperSim, and we previously used Riverbed, and unfortunately they didn't provide academic license anymore. So we are using Exada, which is collaborated with HyperSim, and then to model the communication network, and we use the MATLAB to model the control center. We're trying to investigate this problem in the co-simulation platform. This is partnered with Hydro-Quebec. And this is the attack design, and we're also working on attack mitigation detection as well. So we have, design this attack, and then from operator perspective, how can we detect them? Yeah, that's basically, yeah. Thank you.